Hey, 6th grade, this is Mr. Barris. It's now 3:40 on March 9th, the day before your test, and I wanted to give you guys a review video as promised. I don't have a lot of time. I only have about 20 minutes or so to give you everything you need to know about lessons 1, 2, and 3 in Module 2, or Module I, Unit 2. So, let's get started, and we're going to talk very broadly, so do some studying, don't just watch the video, okay? So this module is broken down into 3 lessons. We had lesson 1, which was on work, energy, and power. Then we had lesson 2, which was on kinetic energy and potential energy. And then we had lesson 3, which was on machines. So that's where we're going. Let's go on to lesson 1, work, energy, and power. So, if you remember work, there was some confusion as to what work is. Work is basically your force on an object times the distance over which you apply that force. Okay? So here's kind of your first equation you need to know. I'm going to call this number 1 for equations. Now, force is always recorded in units of newtons. Distance is always in units of meters. So newtons times meters should get you work, which is always measured in units of joules. Okay? Now, there's a couple requirements for work to happen. Okay? Work always must be done in the direction of the force. Okay? So me lifting a backpack to my shoulders is working because I'm pulling the backpack upwards and the backpack is moving upwards. Okay? Now if I transport a backpack from one end of the room to another end, believe it or not, that is not work because you are using force to lift the backpack up against the force of gravity, but you're not using that force in the same direction as movement if you're carrying it across a room. So that is not work. Work always, always, always must be done in the direction of the force. Okay, cool. Let's talk about energy. Now, there wasn't really any equation for energy, but we defined it. Energy is just the ability to do work. We're going to talk about different kinds of energy in lesson 2, but just remember we had chemical, we had mechanical energy, we have, electromagnetic energy. Don't worry about memorizing each of these to the letter. Just know that energy can come in a lot of different forms, like thermal is another example. We're going to talk about mainly mechanical in our next lesson, lesson 2. So let's keep going. In lesson 1, the next thing we talked about was power. And here's another equation that you need to know. So this is number 2 on your equation list. Power is equal to work over a given amount of time. Okay? So the unit for work, once again, is the joule. The unit for time, once again, is seconds. And power is measured in watts. Okay? So whenever you look at a light bulb in your house, if it says 60 watts or something like that, just remember that 60 watts is the work that's being done divided by the time that the work is done in. Okay? Yeah, you can think about power just as like the efficiency of your work. If you're doing a lot of work in a very small amount of time, you're going to have a huge power rating. If you're not doing a lot of work in a large amount of time, you're going to have a very small power rating. Okay, so it's kind of like the work efficiency. These 3 things, work, energy, and power, that's basically what this lesson was about. Okay, let's go on to lesson 2, which once again was kinetic energy and potential energy. So, lesson 2. Let's define what kinetic energy is first of all. Okay, so kinetics, it comes from a Greek word like kainos or something like that, but kinetic basically means movement. So movement energy is kinetic energy. So any object that is moving has kinetic energy. Okay? So a baseball, an athlete who's running has kinetic energy. Anything that's moving has kinetic energy. Now there's an equation for kinetic energy. So here's number 3 on our equation list. Ke, or kinetic energy, is equal to 1/2 times an object's mass times its velocity squared. Okay? So once again, m is for mass, v is equal to velocity. So you can see that if we were to increase mass, we would increase our kinetic energy. So the bigger our mass gets, the bigger our kinetic energy gets. Similarly, the faster an object is going, the bigger its kinetic energy. So those two things, mass and velocity, both directly influence kinetic energy. Okay, one final note on this equation. The squared sign, I noticed that a lot of you guys didn't really know exponents that well, and I'm not surprised because exponents are kind of a more advanced math concept than maybe what you're used to. Exponents is just another way of saying I'm going to times this number by itself a certain amount of times. Okay? So when we say velocity squared, we're saying, okay, 1/2 times my mass times my velocity 2 times. Okay? So whatever your velocity is times by itself, that is the same thing as velocity squared. So for example, 2 meters per second, when we square that, we get 2 times 2, which gives us 4. Just remember, squared means times that number by itself. Okay, I feel like I've said that enough. Let's go on to potential energy. Potential energy. Actually, let's define it first. Potential energy is just stored energy. So just like the whiteboard marker that I love to play with in class, whenever I'm holding a whiteboard marker above the ground, even though it's not moving, it still has energy stored in it, because as soon as I let it go, it's going to start moving and generating energy. Now we're going to talk about a very specific type of potential energy. Okay, that's called gravitational potential energy. Now I bring this up because every type of energy pretty much has a potential form. When we talk about chemical energy can be stored. It's stored in the foods you eat. We can have stored energy in the photons from the sun. Energy is stored everywhere, but we're only going to talk about mechanical potential energy, which is influenced by gravity. Let me just point out, there is another form called elastic potential energy, which is also mechanical. Elastic energy is basically what's responsible for when you compress a spring or when you pull a spring apart, it wants to snap back into place. That's because you're storing energy when you pull it or press it. And that energy is released when it goes back to its original shape. Okay, but we're mainly going to focus on the gravitational potential energy. Now here's your next formula, number 4 on your list. PE is equal to the mass of an object times its gravitational constant, which is always 9.8, times its height. Okay? So m is mass, g is always 9.8 meters per second squared, and height is in meters. Mass is always in kilograms as well. Okay, I feel like that's a pretty simple equation because you're just timesing three things together, so I'm not going to spend too much time on that. So let's jump right into your fifth equation. Mechanical energy is basically kinetic energy plus potential energy. That's the total mechanical energy of an object. Okay. Cool. Realize you can expand these equations into these forms if you wanted to, but for all intents and purposes we're just going to say ME is equal to KE plus PE. That brings us to lesson 3. Now lesson 3 was the beast of all lessons. There's a lot of stuff covered here and I only have a limited amount of time to cover it in, so I'm just going to try and stick to the basics and rely on you guys to use your notes and your book on the test to do well. Okay? Now a machine. When we think about machines, we are tempted to think about like computers or calculators. That's not really what a machine is in the scientific sense. A machine is basically an object or device. My handwriting is horrible tonight, so I apologize. Object used to change the way we do work. Okay? Now, machines only manipulate or change force and distance. Okay, in other words, they don't even change the amount of work that's done. It's going to take the exact same amount of work to lift a couch into a truck that it would to push a couch into a truck with a ramp. But if we're lifting, we're applying a greater force on the couch over a short distance. If we use a ramp, we're applying less of a force over a greater distance. Okay? But all machines do is manipulate how we use force and distance. Whenever we talk about machines, we always like to talk about their mechanical advantage. Mechanical advantage. Okay, here's another equation for your list. Now this is going to be number 6, I believe. Okay, the mechanical advantage is always equal to the output force divided by the input force. Okay? Now whenever we talk about input and output forces, we're just talking about the forces that we put into a machine and the forces that come out of a machine. Okay? I hope that's clear. Next, we're going to talk about mechanical efficiency. That's always equal to the output work over the input work. Okay? Now, because of conservation of energy, our output work can never be more than our input work. So our efficiency will always be, less than 100%. I forgot this right here. We always times this fraction by 100 to get it to a percentage. But that will always be less than 100%. You're always going to lose some energy. Because we live in the real world. Okay, so this is number 7 on your equation list. Okay, the next part of this lesson covers the different types of simple machines. Now there are 6 of them. We're going to list them and talk about some special things about them. Let me warn you, each machine comes with like its own equation for mechanical advantage. Don't get so hung up on memorizing those. I'm more than likely going to let you use your notes in the test tomorrow. So use the book to your advantage. Don't worry about memorizing them if you can look at your book. So 6 types of simple machines. Number 1, we had what's called a lever. Okay? Now a lever is basically composed of a couple of different things. You have an input force, which I'm going to represent with F sub I. You have a fulcrum, which is a center of rotation. And you have an output force. F out. Okay? So we have our input force, our output force, and our fulcrum. There are three different types of levers, first class, second class, and third class. They're all based on the position of these three items. Okay? This one right here is called a first class lever. Okay? A second class lever is where your fulcrum is at the end. Here's your input force. Well, our input force is just at the end, and our output force is between the input force and the fulcrum. Okay, so the example here was the bottle opener, or the stapler, I believe, was a second class lever as well. This is second class. Don't worry about like the arrows, just remember your output force is always between your input force and the fulcrum. And then the third class, we have, I don't remember how this one goes. Our input force is always between our fulcrum and our output force. Okay, the example of this was a baseball bat. Your body acts as the center of rotation, or the fulcrum. Your hands are pushing on the bat as your input force, and the output force is seen when you hit the ball. Okay? I think there's a formula for mechanical advantage of a lever, and that mechanical advantage formula is basically the distance from input force to fulcrum divided by the distance from fulcrum to output force. Okay? Cool. Let's talk about our next machine. Next we had pulleys. Now pulleys, if you know what a flagpole looks like, you know what a pulley looks like. In this case, we are pulling on an object with a certain force. That object is, in this case, like a rope or a string. And as that rope coils around the pulley, we see, here's our little flag on our flagpole. The rope pulls upward with the same amount of force on the object that's attached to the pulley. Now there are three different types of pulleys. I'm not going to go into each of those right now because we're running short on time, but you'll have your book. I wouldn't worry too much about it though. Let's talk about our next one. We had a wheel and axle. Pretty self-explanatory, but the main thing I want to say here is mechanical advantage of a wheel and axle is equal to the radius of your input force divided by the radius of your output force. Okay? Yeah. Next one, let's talk about an inclined plane, which is basically a glorified name for a ramp. So, you guys know how a ramp works. I already used it in my little truck example. But let's say we have, here's my truck. That's a horrible truck. But we've got a ramp that's used to push things up into a truck, makes things easier by decreasing the force required and increasing the distance over which the object is, pushed. Now, the mechanical advantage of an inclined plane is equal to the length of the ramp or the inclined plane over its height. That's pretty much all I'm going to say about that. Next one, we had our wedge. Okay. Now the wedge is basically like an ice pick or a knife, which when you put a knife or a wedge into an object, you're applying a force downward on it, which causes forces outward from its contact point. So this is used to like split objects. You cut bread to split it apart. You use an axe to chop a tree down and split it apart. Okay? So those are wedges. And then our last one is a screw. So you guys know what a screw looks like. I'm going to try to draw one. It's horrible as usual. Here's like the threads on a screw. The basic thing about a screw is that it's an inclined plane wrapped around a cylinder. It's wrapped around it such that when you turn a screw, you're applying a very small force over a large distance, because that thread, or that inclined plane around the cylinder, it wraps around and around and around and around and around. So it's a very small force over a very large distance. Now, whenever we screw things on to a piece of wood, or whenever you're screwing things together, you do that to secure something in place. So if you imagine like a shelf right here, or a piece of wood that I'm screwing this into, as you apply this small force over a large distance on the screw, your object is going to experience a force that's going to go towards the screw. Okay, righty-tighty, lefty-loosey. Whenever you turn a screwdriver, you're securing this screw inside this object. Okay, so the resulting output force is very large. So I'm going to say F out is large over a small distance. Remember, this is output. This is input. Okay? Alright. Oh gosh, I gotta get going. But I hope this helped you guys get the basics down. If you got any burning questions before our test tomorrow, feel free to come up and ask me. Otherwise, good luck studying. I'm going to see if I can post some practice problems for you right now. And we will talk to you later.